The Sun is burning at 15 million degrees Celsius in its core right now. Not metaphorically burning, not glowing, burning. Nuclear fusion reactions are converting 600 million tons of hydrogen into helium every single second in the Sun's core, releasing energy equivalent to the simultaneous detonation of approximately 100 billion nuclear bombs per second. The energy produced in a single second of solar fusion is enough to power all of human civilization for the next 500,000 years. The Sun has been doing this for 4.6 billion years and will continue doing it for another 5 billion years. The sheer scale of its energy output makes every human concept of heat and power irrelevant as a comparison. That furnace is 150 million kilometers from where you are sitting right now, close enough that you can feel it on your skin on a summer afternoon, close enough that it warms your planet, drives your weather, powers your food chain, and has sustained life on Earth for billions of years. The Sun is not abstract. It is the most consequential physical object in our lives, and it is actively burning at temperatures we cannot meaningfully visualize. And yet, the space between you and the Sun is colder than anything that exists naturally on the surface of Earth. Colder than Antarctica in winter, colder than liquid nitrogen, colder than the far side of the Moon. The average temperature of the space through which sunlight travels on its 8-minute journey from the Sun to Earth is approximately 2.7 Kelvin, 2.7 degrees above absolute zero, the coldest temperature that physics allows anything to be. This is the question we are going to sit with tonight, not skim over, not resolve in one sentence and move on. Sit with. Because the answer to how space can be cold when the Sun is hot is not a single answer. It is a series of answers, each revealing something deeper about what heat actually is, what temperature actually means, what space actually contains, and what it means to be warm or cold in a universe where the ordinary concepts we use for temperature turn out to apply only in the narrow range of conditions that happen to characterize the surface of one small rocky planet. Before we begin, if you put this on because you need something to fill the quiet hours, stay with it. What follows will change how you think about something you experience every time you step outside. Let us start at the beginning. Let us start with what heat actually is, because the answer to the central question of this video depends entirely on understanding something that most people think they already know, and mostly do not. Heat is not a substance. This seems obvious now, but it was not obvious to scientists until the 19th century. Before that, the dominant theory of heat was that it was a fluid, a real physical substance called caloric that flowed from hot objects to cold ones, and that made things hot by being present in them, and cold by being absent. The caloric theory explained a lot. It explained why heat flows from hot to cold. It explained why things expand when heated. It was a coherent and internally consistent model that was used successfully by engineers designing the first steam engines. It was also completely wrong. In 1798, Benjamin Thompson, a physicist and military administrator who went by the title Count Rumford, was supervising the boring of cannon barrels at a military arsenal in Bavaria. He noticed that the friction of boring produced enormous amounts of heat, far more than the caloric theory could account for. The metal shavings were the same temperature as the bulk metal. The heat did not seem to be coming from anywhere. It was being created by the mechanical work of drilling. Thompson concluded that heat could not be a fluid that flowed from one place to another. it had to be something generated by motion, by the mechanical work being done. It took another half-century for this insight to be fully developed into what we now call the kinetic theory of heat. The kinetic theory says that heat is not a substance. Heat is the collective kinetic energy of particles, atoms and molecules in a material. A hot object is an object whose atoms and molecules are moving fast. A cold object is an object whose atoms and molecules are moving slowly. Temperature is a measure of the average kinetic energy of the particles in a system. When a hot object transfers heat to a cold one, what is actually happening is that the fast-moving particles in the hot object are colliding with the slow-moving particles in the cold one, transferring kinetic energy through collisions until both objects reach the same average particle speed, which we call thermal equilibrium. This insight that temperature is not about something a material has, but about something its particles are doing, is the key to understanding why space is cold. Because temperature, defined this way, requires something very specific. It requires particles, moving particles, particles that can collide with each other, transfer kinetic energy to each other, and establish a collective average motion that we can call a temperature. What happens to temperature when there are no particles, or almost no particles? What happens to heat in a vacuum? Space is not a perfect vacuum. As we have established in other contexts, the interstellar medium contains approximately 1 atom per cubic centimetre on average. The solar wind carries protons and electrons outward from the Sun at speeds of 400 to 800 kilometers per second. The cosmic microwave background fills all of space with photons at an energy corresponding to 2.7 Kelvin. None of these make space truly empty. But space is close enough to empty that the concept of temperature becomes strange when applied to it. Consider what happens to heat transfer in space. On Earth, heat moves by 3 mechanisms: conduction, convection, and radiation. Conduction is the transfer of kinetic energy through direct particle contact. Touching a hot stove burns your hand because the fast-moving particles in the metal transfer their kinetic energy to the particles in your skin through physical contact. Convection is the transfer of heat through the bulk movement of a fluid. The hot air above a radiator rises, carrying its thermal energy with it. Radiation is the transfer of heat through electromagnetic waves, infrared photons emitted by any warm object that carry energy through space without requiring a medium to travel through. In space, conduction and convection are essentially impossible. There are no particles to conduct through and no fluid to convect. Radiation is the only mechanism by which heat can be transferred across the vacuum of space. This is profoundly important because radiation behaves very differently from conduction and convection. Conduction and convection warm the medium they travel through. Hot air rising from a radiator warms the air it passes through. A hot metal rod conducts heat continuously along its length, warming every point it touches. Radiation does not work this way. Electromagnetic radiation, including the infrared radiation from the Sun, the visible light from the Sun, and the ultraviolet radiation from the Sun, travels through the vacuum of space without warming it. The photons pass through the vacuum without interacting with it, because there is essentially nothing in the vacuum to interact with. The energy is not deposited in the space, it is deposited in whatever object eventually absorbs the radiation. This is the core of the answer. The Sun heats things. It does not heat space. The Sun's radiation travels through space without warming it, and deposits its energy in whatever objects it hits: planets, asteroids, dust grains, spacecraft, your skin on a summer afternoon. Between those objects is space that is not being heated, because radiation does not heat vacuums. The space between the Sun and Earth is not warmed by the Sun's radiation passing through it. It is simply passed through. This can feel counterintuitive because on Earth we experience sunlight as warming the air. Stand in direct sunlight on a clear day and you feel warm. Step into shade and you feel cooler immediately. It seems as though sunlight is warming the air as it passes through it, but this is not quite what is happening. Sunlight passes through clear, dry air without interacting with it significantly. Clear air is largely transparent to visible light. What warms you when you stand in sunlight is the direct absorption of solar radiation by your skin, the photons hitting your skin and depositing their energy there. The air around you feels warmer in sunlight, partly because the ground and surfaces around you are being warmed by solar radiation and are then transferring that heat to the air through conduction and convection. The air itself is relatively transparent to sunlight and is mostly warmed from below, from the warm ground, rather than directly from sunlight passing through it. If you could stand in space, in a spacesuit with no atmosphere around you, in direct sunlight at Earth's distance from the Sun, the sunlit side of your suit would become extremely hot because it would be absorbing all the solar radiation hitting it with no air to convect the heat away. The shaded side of your suit would become extremely cold because it would be radiating infrared energy into space with nothing coming back from the cold sky to balance the loss. The difference between the sunlit and shaded sides could be several hundred degrees Celsius, far more extreme than any temperature difference experienced on Earth's surface, where the atmosphere moderates the extremes by distributing heat through convection and conduction. This is exactly what happens on the Moon. The Moon has no atmosphere, nothing to moderate the temperature extremes, nothing to conduct heat from the sunlit side to the shaded side, nothing to convect warm air to equalize temperatures. The surface of the Moon in direct sunlight reaches approximately 127 degrees Celsius, hot enough to boil water if there were any water to boil. The surface of the Moon in shadow drops to approximately minus 173 degrees Celsius, colder than liquid nitrogen. And these extreme temperatures exist simultaneously, just centimeters apart, at the boundary between sunlit and shadowed surface. The Sun is heating the sunlit half of the Moon intensely, and the shaded half is radiating its stored heat into space and getting nothing back. The space between these two surfaces, even the space just a meter above the Moon's surface, is cold. Whatever temperature we assign to that space, whether we measure the 2.7 Kelvin of the cosmic microwave background photons passing through it, or the slightly elevated temperature of the thin envelope of solar wind particles above the surface, it is cold relative to the sunlit surface below it. The Sun's radiation has passed through that space on its way to the surface and heated the surface. It has not heated the space. Now let us go deeper. Because the explanation we have given so far, radiation passes through vacuum without warming it, is correct but incomplete. It addresses why space does not warm up from sunlight passing through it. It does not fully address why space is so cold in the first place, why it has the background temperature of 2.7 Kelvin rather than 0 or some other value. To understand that, we need to understand where the 2.7 Kelvin comes from and what it means. The 2.7 Kelvin background temperature of space is the temperature of the cosmic microwave background, the afterglow of the Big Bang, that fills all of space uniformly in every direction. This radiation was produced approximately 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form, and the opaque plasma of the early universe became transparent. At that moment, photons that had been trapped in the plasma were suddenly free to travel. They have been travelling ever since, for 13.4 billion years, and as the universe has expanded, the wavelengths of these photons have been stretched proportionally, shifting them from the visible light they originally were to the microwave radiation they are now. The expansion of the universe has cooled this radiation from the approximately 3000 Kelvin it had when it was released to the 2.7 Kelvin it has today. This means that the coldness of space, the 2.7 Kelvin background, is not simply the absence of warmth. It is the presence of the universe's oldest light, stretched and cooled by billions of years of cosmic expansion, filling all of space with a faint whisper of energy that represents the minimum temperature anything in the universe can cool down to by radiating energy away. An object in the deepest intergalactic void, far from any star or galaxy, will radiate infrared photons and lose energy until it reaches 2.7 Kelvin. It cannot cool below that because the cosmic microwave background is constantly delivering 2.7 Kelvin worth of energy to it from all directions. This is the floor, the minimum, the coldest anything can get in the current universe without some external mechanism of active cooling. And the space between stars, even the space between the Sun and Earth, is at this floor. Despite the Sun blazing at 15 million degrees in its core and 5,778 Kelvin at its surface, despite all that energy pouring outward in every direction at the speed of light, the vacuum of interplanetary space sits at essentially the background temperature of the universe. The sunlight passes through. The space itself stays cold. This is perhaps the most profound aspect of the answer. The Sun does not warm space. It cannot warm space. Not because it is not powerful enough. The Sun's total power output is 3.8 times 10 to the 26 watts, a number so large it is essentially meaningless in human terms. But because space cannot be warmed by radiation in the way that matter can, the photons pass through. They carry energy, but they carry it from the Sun to objects, not to space. Space itself is not an object in the relevant sense. It is the absence of objects, and you cannot heat an absence. Or, more precisely, the extremely sparse contents of space absorb so little of the radiation passing through them that their temperature remains negligibly different from the background. The solar wind particles, protons and electrons streaming outward from the Sun at hundreds of kilometers per second, do carry thermal energy. Their temperature is actually extremely high. The solar wind plasma near Earth has temperatures in the range of 100,000 to several million Kelvin, depending on which component you measure. But this high temperature is deceptive. Temperature in a plasma measures the average kinetic energy per particle. The solar wind plasma near Earth has extremely energetic particles, but there are so few of them per cubic centimetre that the total thermal energy in any given volume of space is negligible. A cubic metre of solar wind plasma near Earth contains approximately 10 million particles, vastly more than in the deep interstellar medium, and yet so much less than any volume of gas on Earth that comparing temperatures is almost meaningless. Temperature and heat are different things. A gas at 1 million Kelvin with 1 million particles per cubic metre contains far less thermal energy than a gas at 300 Kelvin with 10 to the 25 particles per cubic meter, because total thermal energy is proportional to temperature times the number of particles, and the far greater number of particles in the low temperature gas overwhelms the high temperature of the sparse plasma. A cubic meter of air at room temperature contains vastly more thermal energy than a cubic meter of solar wind plasma at 1,000,000 Kelvin. If you put a thermometer in the solar wind, the electrons and protons would hit it with high individual energies, but so few of them per second that the thermometer would cool by radiation faster than the rare particle collisions could warm it. The thermometer would eventually stabilize near the 2.7 Kelvin of the cosmic microwave background, not at the 1,000,000 Kelvin temperature of the surrounding plasma. This is the distinction between temperature as a property of individual particles and temperature as a macroscopic quantity meaningful for objects. In physics, we can define temperature in multiple ways, and in dilute plasmas and in space, the different definitions can give dramatically different answers. A spacecraft in solar orbit near Earth experiences an effective temperature determined by the balance between the solar radiation it absorbs and the infrared radiation it emits, an effective temperature of roughly 250 to 300 Kelvin, depending on its surface properties, comparable to Earth's surface temperature. It does not experience the 1,000,000 Kelvin temperature of the solar wind plasma it is embedded in, because there are so few solar wind particles hitting it per second that their contribution to its thermal budget is negligible compared to the solar radiation it absorbs and the infrared it emits. The temperature of an object in space depends on what it absorbs and what it emits. It is not determined by the temperature of the sparse medium surrounding it in the way that a pot of water's temperature is determined by the boiling water surrounding it. In a dense medium like water or air, the surroundings dominate because they can transfer heat efficiently through conduction and convection. In the sparse medium of space, each object reaches its own equilibrium temperature independently, determined by its own absorption and emission properties relative to the radiation field it is embedded in. This is why the Moon's sunlit surface is 127 degrees Celsius and its shaded surface is minus 173 degrees Celsius, while the space above both surfaces is at 2.7 Kelvin. The sunlit surface absorbs solar radiation and reaches a temperature where its own infrared emission balances the absorbed energy. The shaded surface emits infrared radiation and cools until it nearly reaches the cosmic background temperature. It would reach exactly 2.7 Kelvin eventually if the Moon never rotated into sunlight. The space above both surfaces is at the cosmic background temperature because it has too few particles to absorb significant radiation and reaches equilibrium with the universal background. Now let us talk about the corona. Because the Sun's outer atmosphere provides perhaps the most dramatic illustration of the paradox at the heart of this question, and it remains one of the most actively debated problems in solar physics. The Sun's surface, the photosphere, has a temperature of approximately 5,778 Kelvin. This makes intuitive sense. The Sun is losing energy by radiation, and the photosphere is the outermost layer from which that radiation escapes freely to space. Its temperature can be understood in terms of the balance between the energy flowing outward from the core and the energy being radiated away at the surface. Just above the photosphere is a layer called the chromosphere, a relatively thin layer a few thousand kilometers thick, where the temperature rises from 5,778 Kelvin at the photosphere boundary to approximately 20,000 Kelvin at its outer edge. Already the temperature is going the wrong way. You would expect the atmosphere to cool as you move away from the heat source, Instead, it heats up. Above the chromosphere is the corona, the Sun's outer atmosphere extending millions of kilometers into space, visible to the naked eye only during total solar eclipses, as the pearlescent glow surrounding the dark disk of the Moon. The corona has a temperature of approximately 1 to 3 million Kelvin. Occasionally, in active regions associated with sunspots, temperatures of up to 10 million Kelvin have been measured. The corona is hundreds of times hotter than the solar surface below it. This violates everything you might expect from a simple understanding of how heat works. The source of energy is the core. The core is at 15 million Kelvin. Moving outward from the core, the temperature drops through the radiative zone and the convective zone and the photosphere, going from 15 million to 5,778 Kelvin. Then it reverses. The chromosphere heats up to 20,000 Kelvin. The corona heats up to 1 to 3 million Kelvin. Then, moving further out into the solar wind, the temperature drops again, though it remains far higher than you would expect from simple expansion cooling. This is the coronal heating problem, and it has been one of the central unsolved problems in solar physics for decades. It was identified clearly in the 1940s when spectroscopic observations revealed that the corona contained highly ionized iron atoms, ions from which 13 electrons had been stripped. Stripping 13 electrons from an iron atom requires temperatures of millions of degrees. The corona is genuinely at million Kelvin temperatures. This is not a measurement error or a calibration artifact. It is real. The question is why. The reason matters for our broader question because the corona's extreme temperature is a direct consequence of the Sun's magnetic field and of energy transport processes that have nothing to do with simple radiation heating. Understanding why the corona is hot illuminates why space is cold. It reveals the specific mechanisms by which the Sun transfers energy to nearby matter, and by which that matter heats up or stays cold, depending on what mechanisms are available to it. Several mechanisms have been proposed for coronal heating. Wave heating proposes that magneto-hydrodynamic waves, oscillations in the plasma driven by convective motions in the Sun's surface, propagate upward along magnetic field lines into the corona and deposit their energy there through wave damping. Nanoflare heating proposes that countless tiny magnetic reconnection events, small-scale explosions where oppositely directed magnetic field lines snap and reconnect, collectively heat the coronal plasma to million Kelvin temperatures. Reconnection events release magnetic energy as kinetic energy of the plasma and as direct particle acceleration. And if enough small events occur frequently enough, they could maintain the corona's temperature against the energy lost through radiation. Both mechanisms are likely important, and neither is sufficient alone to fully explain coronal heating. The Parker Solar Probe, launched by NASA in 2018 and currently the fastest and closest solar observatory ever built, is actively investigating these mechanisms by flying through the solar corona itself, reaching distances closer to the Sun than any previous spacecraft, and measuring the properties of the plasma, the magnetic field, and the wave activity directly. The Parker Solar Probe has already made significant contributions. It has directly detected Alfvén waves, a specific type of magneto-hydrodynamic wave, in the solar corona at amplitudes and frequencies consistent with being a major contributor to coronal heating. It has detected magnetic field switchbacks, sudden reversals in the direction of the magnetic field, followed by returns to the original direction, that are associated with jets of faster solar wind and that may indicate localized reconnection events. It has measured the acceleration of the solar wind in the inner corona with unprecedented detail, finding that the acceleration occurs closer to the Sun than previous models predicted. This is real ongoing science, not settled, not complete, actively being done by real scientists with real spacecraft collecting real data. The coronal heating problem is one of the most extensively studied problems in astrophysics, and it remains genuinely open, not because scientists have not thought hard about it, but because the corona is a complex magnetized plasma system with multiple interacting physical processes, and definitively identifying the dominant heating mechanism requires measurements that have only recently become possible. What is certain is that the corona's million Kelvin temperature is maintained by non-radiative energy transfer from the solar interior, by waves and magnetic reconnection, rather than by the simple outward flow of thermal radiation that heats the photosphere. This is why the coronal heating paradox exists. The photosphere is heated by radiation flowing outward from the core. The corona is not directly connected to that radiative energy flow. It is too thin and too extended for radiative heating to account for its temperature. It is instead heated by mechanical and magnetic energy that takes a very different path from the core to the corona. And, crucially, this coronal energy does not heat space beyond the corona either. The million Kelvin plasma of the corona expands outward into the solar wind, but as it does, it cools through adiabatic expansion, the same process that makes a spray can feel cold when you use it, and that makes air cool as it rises in the atmosphere. By the time the solar wind reaches Earth, it has cooled from coronal temperatures to approximately 100,000 Kelvin, and the density has dropped so dramatically that, as we discussed, a spacecraft embedded in it reaches its own equilibrium temperature, determined by solar radiation rather than by the solar wind plasma temperature. The Sun is hot. Its corona is extraordinarily hot. Hot enough to fully ionize heavy elements, hot enough to drive the solar wind. And the solar wind extends throughout the solar system, carrying that hot plasma outward. And still, space is cold, because hot plasma does not make space hot when the plasma is dilute enough that it cannot efficiently transfer its heat to objects passing through it. Because radiation heats objects, not space. Because temperature in a sparse medium is a meaningless concept for the purposes of describing whether things placed in that medium will be warm or cold. Let us now talk about what happens to heat in a perfect vacuum, in a space with absolutely no particles at all, because this thought experiment illuminates something fundamental about the nature of temperature and the limits of the concept. In a perfect vacuum, there are no particles, no atoms, no molecules, no electrons, no protons, just empty space. What is the temperature of a perfect vacuum? The answer is that the question is ill-defined. Temperature is a statistical property of collections of particles. It is the average kinetic energy per particle in a system. A system with no particles has no average kinetic energy per particle because there are no particles to average over. Temperature is undefined. Not zero, not infinite. Undefined. Like asking what the average height of a group of 0 people is. This is philosophically important because it means that the cold of space is not actually a temperature in the same sense as the temperature of an ice cube or a planet's surface. The 2.7 Kelvin of the cosmic microwave background is real. It is the temperature of the photon gas filling space, the thermal radiation field in which all objects in the universe are embedded. But the temperature of the space itself, of the vacuum between the photons, is undefined. Space does not have a temperature. Objects in space have temperatures determined by their interaction with the radiation field and with any particles they encounter. But space itself, the vacuum, is not a thermodynamic system with a temperature. This means that when we say space is cold, we are speaking somewhat loosely. We mean that objects placed in space with no other energy input will cool by radiating infrared photons until they reach equilibrium with the cosmic microwave background at 2.7 Kelvin. We mean that there are essentially no particles in space to transfer thermal energy to a thermometer by conduction. We mean that the radiation field of space is at 2.7 Kelvin, cold by any Earth standard. We do not mean that space has a temperature in the precise thermodynamic sense that a cup of water has a temperature. But the practical consequences of this coldness are real. An object placed in deep space with no radiation input, shielded from all stars and galaxies, will cool by radiation until its surface temperature reaches 2.7 Kelvin. At that temperature, its outgoing radiation exactly balances the incoming cosmic microwave background radiation. It is in equilibrium. It is genuinely cold, colder than liquid helium, colder than any naturally occurring temperature on Earth's surface. This is the cold that space probes experience. This is the cold that engineers must protect spacecraft electronics against. This is the cold that astronauts in the shadow of a planet experience, not metaphorically, but physically, as the heat stored in their suits and equipment bleeds away by radiation into the darkness. And this cold exists 4 minutes of light travel time from a star burning at 15 million degrees. On the other side of nothing. Separated from that furnace by a vacuum so perfect that the heat cannot cross it except as radiation, and radiation cannot warm space itself, only the objects in it. Let us talk about what this means for the practical experience of being in space. Because the physics we have been discussing is not abstract, it has concrete consequences for human beings who leave Earth's atmosphere and enter the environment we have been describing. And those consequences are stranger and more counterintuitive than most accounts of spaceflight convey. The first thing that surprises most people when they think carefully about temperature in space is that the problem is not staying warm, the problem is staying cool. This seems wrong. Space is cold. The temperature of the cosmic background is 2.7 Kelvin. Surely the challenge is preventing astronauts from freezing. But this is a misapplication of Earth intuitions to a space environment. On Earth, staying warm requires insulation against conductive and convective heat loss, because the air around you is continuously drawing heat away from your body through contact. In space, there is no air. There is no convective or conductive heat loss. An astronaut in a spacesuit is surrounded by vacuum, a perfect insulator against conduction and convection. The human body generates approximately 80 to 100 watts of metabolic heat continuously. In normal Earth conditions, this heat is removed by the surrounding air through convection and by radiation from the skin. In a spacesuit, in the vacuum of space, convective cooling is impossible. The only mechanisms for heat removal are radiation from the suit's surface and evaporation of sweat, which requires the suit's life support system to actively manage. Without active cooling, the metabolic heat generated by an astronaut's body would accumulate. The suit and its occupant would get progressively hotter, not colder, hotter. This is counterintuitive, but physically correct. The vacuum of space is an extraordinarily effective insulator against heat loss by the mechanisms we normally rely on. The engineering challenge of human spaceflight is not heating astronauts, but cooling them, removing the heat generated by their bodies and their equipment and dumping it into space through radiation. The International Space Station faces this challenge at enormous scale. The station's electronics, computers, exercise equipment, food preparation systems, lighting, and the metabolic output of its crew all generate heat that must be removed. The station uses a complex liquid cooling system, water loops inside the pressurized modules collecting heat from equipment and crew, heat exchangers transferring that heat to ammonia loops outside the station, and large radiator panels radiating the ammonia's heat away as infrared radiation into space. The radiators are among the most critical components of the station's life support system. If they fail, the interior of the station heats to dangerous temperatures within hours. The radiators work by exploiting the only heat transfer mechanism available in space: radiation. A warm surface radiates infrared photons in all directions. If the surface is pointed away from the sun, toward the cold, dark sky rather than toward the solar radiation source, it can dump heat into space. The rate of heat radiation depends on the fourth power of the surface temperature, according to the Stefan-Boltzmann law. A surface at room temperature, about 300 Kelvin, radiates about 460 watts per square meter. The station's radiators have a total area of approximately 1,500 square meters, giving a total radiative cooling capacity of roughly 70 kilowatts under ideal conditions, enough to handle the station's heat load under normal operations. This is the thermal engineering of space. Not heating against cold, cooling against the insulating properties of vacuum. The challenge is dumping heat efficiently into a medium that will only accept it as radiation, at a rate that can keep up with the heat generated by the systems you need to operate. Spacecraft thermal engineering is one of the most complex aspects of mission design, precisely because of this challenge. Every surface of a spacecraft must be carefully designed for its thermal properties. Surfaces that face the sun must be protected against overheating, typically using white paint or reflective gold foil that reflects most solar radiation rather than absorbing it. Surfaces facing away from the sun that need to shed heat use high emissivity materials that radiate infrared efficiently. Surfaces connecting hot and cold regions of the spacecraft must be designed with appropriate thermal conductance, enough to allow heat to flow to the radiating surfaces, but not so much that cold side components are warmed by proximity to hot side components. The gold foil that you see wrapping many spacecraft, the crinkled reflective material covering much of Voyager, Hubble, and many other missions, is not decoration. It is thermal control blanket. Multi-layer insulation consisting of many thin layers of aluminized polyamide film designed to minimize both the absorption of solar radiation and the emission of infrared radiation. By minimizing both, the thermal control blanket keeps the spacecraft interior near room temperature, despite the enormous temperature swings between sunlit and shaded configurations. Webb's thermal architecture is the most extreme example of spacecraft thermal engineering ever executed. We discussed the 5-layer sun shield designed to keep the telescope cold. The reason for the extreme cold is not comfort, it is sensitivity. Webb's infrared detectors must operate at temperatures below -233 degrees Celsius to be sensitive to the faint infrared light of distant galaxies. If the detectors were at room temperature, they would glow so brightly in the infrared from their own thermal emission that they would be blinded, unable to detect anything from the sky. The extreme cold is required for the detectors to function at all. Webb achieves this cold passively, not through active refrigeration, but through the sun shield geometry that allows the telescope side to radiate its heat to cold space while shielding it from solar, Earth, and Moon radiation. The detectors on Webb's MIRI instrument, the mid-infrared instrument that made the Alpha Centauri observation we discussed require even colder operating temperatures than the passive cooling can achieve. They use a closed-cycle cryocooler that actively pumps heat from the detectors at -266 degrees Celsius to the passively cooled structure at -233 degrees Celsius. This cryocooler, operating continuously throughout the mission, is responsible for making MIRI's sensitivity possible. All of this engineering, the sun shields, the thermal control blankets, the radiators, the cryocoolers, exists because of the fundamental physics we have been discussing. Because space is cold but not uniformly cold. Because sunlight is intense but heats only what it hits. Because vacuum insulates perfectly against conduction and convection. Because radiation is the only heat transfer mechanism and it depends on geometry. Which surfaces face the sun and which face cold, dark space, in ways that create enormous temperature gradients within small volumes. Let us now talk about planetary atmospheres, because the difference between the Moon's extreme temperature swings and Earth's temperate climate is entirely a consequence of atmosphere. And understanding this difference illuminates how atmospheres mediate the relationship between stellar radiation and surface temperature. We established that the Moon, without an atmosphere, experiences temperature swings from +127 to -173 degrees Celsius, depending on whether a given surface point is in sunlight or shadow. The Earth, at the same distance from the Sun, with the same basic solar radiation input, maintains an average surface temperature of approximately 15 degrees Celsius, and temperature differences between equatorial and polar regions, between day and night, between summer and winter, that are moderate compared to the Moon's extremes. Earth's poles in winter do not approach -173 degrees Celsius. Earth's equatorial desert in summer does not approach +127 degrees Celsius. The difference is the atmosphere. Earth's atmosphere moderates temperature extremes through several mechanisms working simultaneously. The most direct is the greenhouse effect. The atmosphere is largely transparent to incoming solar radiation, mostly visible light, allowing it to reach the surface. But the atmosphere is not transparent to the infrared radiation that the warm surface emits back upward. Molecules of water vapor, carbon dioxide, methane, nitrous oxide, and ozone absorb outgoing infrared radiation and re-emit it in all directions, including back down toward the surface. This traps heat in the lower atmosphere. The infrared photons cannot escape directly to space, but are repeatedly absorbed and re-emitted by greenhouse gas molecules, extending their effective path to space and warming the surface beyond what it would be without this trapping. Without any greenhouse effect, Earth's average surface temperature would be approximately -18 degrees Celsius, cold enough that most of Earth's surface would be frozen and liquid water would be scarce. The natural greenhouse effect, dominated by water vapor with significant contributions from carbon dioxide and other gases, raises the average surface temperature from -18 to +15 degrees Celsius. A 33-degree warming from the natural greenhouse effect is what makes Earth habitable. The atmosphere also moderates temperature by distributing heat through convection and wind. Warm air at the equator rises and moves toward the poles, carrying thermal energy poleward. The oceans do the same. Warm ocean currents at the surface carry heat from tropical regions toward higher latitudes, moderating polar temperatures. The result is that Earth's poles are far warmer than they would be if the planet received only the solar radiation directly incident on polar latitudes, a sun that never rises very high in the sky and that disappears entirely in winter. The polar regions are warmed in part by heat transported from the tropics by atmospheric and oceanic circulation. Mars provides an instructive intermediate case. Mars has an atmosphere, primarily carbon dioxide, but it is very thin, with a surface pressure approximately 0.6% of Earth's. This thin atmosphere provides some greenhouse warming, but very little atmospheric buffering of temperature extremes. Martian surface temperatures swing from approximately -125 degrees Celsius at the poles in winter to approximately +20 degrees Celsius at the equator in summer. These swings are more extreme than Earth's, but less extreme than the Moon's, reflecting an intermediate level of atmospheric moderating effect. Venus presents the opposite extreme. Venus has an atmosphere approximately 90 times denser than Earth's, nearly 100 times the surface pressure, composed primarily of carbon dioxide with sulfuric acid clouds. This dense carbon dioxide atmosphere produces an extreme greenhouse effect. Venus receives less solar radiation per square metre than Earth. It is closer to the Sun, but its thick clouds reflect approximately 70% of incoming solar radiation back to space. Yet the Venusian surface temperature averages approximately 465 degrees Celsius, hot enough to melt lead, hot enough that the surface temperature barely changes between day and night, despite Venus having an extremely slow rotation. The greenhouse effect on Venus is so powerful that the entire planet is effectively at a uniform, searing temperature, regardless of location or time of day. These planetary comparisons, Earth, Moon, Mars, Venus, illustrate the spectrum of how atmospheric properties interact with solar radiation to determine surface temperature. The Moon, with no atmosphere, produces extreme temperature contrasts driven purely by the geometry of solar illumination. Earth, with a moderate atmosphere, moderates these contrasts to a habitable range through greenhouse warming and heat distribution. Mars, with a thin atmosphere, has intermediate behavior. Venus, with an extreme atmosphere, has runaway greenhouse warming that has made it uninhabitable despite being in the same solar system and at a roughly similar distance from the Sun as Earth. The concept of the habitable zone, the range of orbital distances from a star within which liquid water can exist on a planetary surface, is fundamentally a statement about this balance between stellar radiation input and atmospheric greenhouse effect. A planet at the inner edge of the habitable zone is one where the greenhouse effect, combined with the stellar radiation, raises the surface temperature to the boiling point of water. A planet at the outer edge is one where the stellar radiation, combined with the most extreme greenhouse effect an atmosphere can sustain without losing molecules to space, is just barely sufficient to keep water liquid at the surface. Earth sits comfortably within the Sun's habitable zone, with an atmosphere that both provides greenhouse warming and moderates temperature extremes through circulation. The result? A planet whose average surface temperature has remained within the range compatible with liquid water for billions of years, is what has allowed the continuous development of life from its origins approximately 4 billion years ago to the present. This stability is not guaranteed. The Sun is slowly brightening. It is approximately 30% more luminous today than it was when Earth formed 4.6 billion years ago, and will continue to brighten over the next several billion years. The geological carbon cycle, the process by which carbon dioxide is removed from the atmosphere by weathering reactions and returned by volcanic outgassing, acts as a thermostat, drawing down atmospheric CO2 when temperatures rise and allowing it to build up when temperatures fall, buffering the surface temperature against the slowly increasing solar output. This geological thermostat is why Earth has remained habitable through the 4.6 billion years of increasing solar luminosity, rather than having experienced runaway warming as the sun brightened. The fragility of this system, the delicacy of the balance between solar radiation, greenhouse effect, and geological carbon cycling that keeps Earth habitable, is one of the things that makes the question of habitable planets around other stars so complex. It is not sufficient for a planet to be in the right orbital range from the right type of star. It must also have an atmosphere of the right composition and density. It must have a geological system capable of regulating that atmosphere over billion-year timescales. It must have a magnetic field strong enough to prevent the stellar wind from stripping the atmosphere away over those same timescales. It must not experience catastrophic impacts or volcanic events that fundamentally alter the atmospheric composition before life has time to emerge and diversify. The specificity of the requirements is one of the arguments for life being rare even in a universe full of habitable zone planets. Having the right orbit is necessary but not sufficient. The atmosphere must work out. The geology must work out. The magnetic field must work out. The impact history must work out. Many planets in habitable zones around many stars may fail one or more of these requirements and remain airless or scorching or frozen despite their favourable orbital locations. The Moon is in Earth's habitable zone. It orbits at the same distance from the Sun as Earth, and its surface is alternatively scalding and freezing, depending on whether sunlight is falling on it. The difference between the Moon and Earth is the atmosphere, and the atmosphere is not guaranteed. It is a product of the planet's geological history, its mass, its composition, its magnetic field, and a sequence of events over billions of years that could easily have gone differently. Now let us talk about the specific numbers that describe how solar energy distributes through the solar system. Because the inverse square law that governs how solar radiation weakens with distance from the Sun is directly relevant to understanding why the outer solar system is cold despite the Sun's enormous power output. The Sun emits energy at a rate of approximately 3.8 times 10 to the 26 watts, its total luminosity. This energy radiates outward in all directions from the solar surface, spreading over ever larger spheres as it travels outward. The surface area of a sphere is 4 times pi times radius squared. As distance from the Sun increases, the sphere over which the Sun's energy is distributed grows as the square of the distance. The energy per unit area, the solar irradiance, decreases as the inverse square of the distance. At Earth's distance, 1 astronomical unit, the solar irradiance is approximately 1,361 watts per square metre. This is called the solar constant, and it is the energy available to Earth's climate system per square metre of cross-section perpendicular to the Sun's direction. At Mars's distance, approximately 1.52 astronomical units, the solar irradiance is approximately 590 watts per square metre, about 43% of what Earth receives. This reduction contributes to Mars being colder than Earth even before accounting for its thinner atmosphere. At Jupiter's distance, approximately 5.2 astronomical units, the solar irradiance drops to approximately 50 watts per square metre, less than 4% of what Earth receives. Jupiter is approximately 778 million kilometers from the Sun, and yet receives so little solar energy per square meter that its atmosphere is dominated by its own internal heat. Jupiter radiates more heat outward than it receives from the Sun, powered by the slow gravitational contraction of its interior. At Neptune's distance, approximately 30 astronomical units, the solar irradiance drops to approximately 1.5 watts per square meter, about 0.1% of what Earth receives. Neptune is so far from the Sun that it would be nearly dark there. Sunlight at Neptune is roughly equivalent to being on the shaded side of a building in full daylight on Earth. Neptune's atmosphere is extremely cold. Cloud top temperatures of approximately -200 degrees Celsius, and its blue color comes from methane in the atmosphere absorbing red light. Neptune also radiates more heat than it receives from the Sun, its internal heat from formation, still slowly leaking out 4.6 billion years later, provides more energy to its atmosphere than the distant Sun does. Beyond Neptune, in the Kuiper belt and the Oort cloud, solar irradiance drops to negligible levels. The surfaces of Kuiper belt objects like Pluto and Eris receive so little solar energy that they are coated in ices of nitrogen and methane and carbon monoxide that remain solid under the faint illumination. Pluto's surface temperature averages approximately -229 degrees Celsius, close to the cosmic background temperature of -270 degrees Celsius. The Sun, from Pluto, appears as a bright star, distinguishable from other stars by being by far the brightest point in the sky, but not appearing as a disk to the naked eye, and not providing warmth that would be felt on the skin. This progression from 1,361 watts per square meter at Earth to 1.5 watts at Neptune to fractions of a watt in the outer solar system illustrates how the Sun's enormous energy output is diluted by distance. The inverse square law is unforgiving. Doubling your distance from the Sun quarters your received energy. Going from Earth to Saturn, approximately 10 times Earth's distance, reduces the solar irradiance by a factor of 100. The Sun is enormously powerful, but the solar system is enormously large, and the energy spreads through an ever-growing sphere as it travels outward. At the distance of the nearest star, Proxima Centauri, at 4.24 light-years, or approximately 268,000 astronomical units, the Sun's irradiance has dropped to approximately 2 times 10 to the -13 watts per square meter. Essentially nothing. The Sun, as seen from Proxima Centauri, is a bright star but contributes negligible energy to any planet or object orbiting Proxima. The solar system ends, in any meaningful thermal sense, long before you reach the nearest star. And in the space between, in the 4 light-years of interstellar void between our solar system and Proxima, there is no significant radiation from the Sun or from Proxima. The cosmic microwave background provides its universal 2.7 Kelvin. Occasional photons from distant galaxies contribute negligibly. Cosmic rays pass through, high energy but rare. The space is cold not merely because it is far from the Sun, but because there is essentially no energy source of any kind to warm it. It sits at the minimum temperature that physics allows, the floor set by the ancient afterglow of the Big Bang, permeating the universe uniformly from all directions. Let us now talk about the temperature of stars themselves, because we have been treating the Sun's temperature as a given without examining what it means for a star to be at a certain temperature, and why different stars have dramatically different temperatures despite undergoing the same basic nuclear fusion process. A star's surface temperature, the temperature of the photosphere that we can actually observe, is determined by the balance between the total energy the star produces in its core and the surface area through which it radiates that energy. A star producing more total energy than the Sun must radiate more energy per square meter from its surface to maintain thermal equilibrium, which means its surface must be hotter. A star producing less energy than the Sun, or a star with a much larger surface area, will have a cooler surface. The temperature of a star's photosphere determines its color. Objects in thermal equilibrium emit radiation across a continuous spectrum whose peak wavelength is inversely proportional to temperature. Hotter objects peak at shorter wavelengths, cooler objects at longer wavelengths. This is called blackbody radiation, and it is described quantitatively by Planck's law. The Sun's photosphere at 5,778 Kelvin peaks in visible light, specifically at yellow-green wavelengths. This is not a coincidence. Human eyes evolved to be maximally sensitive in exactly the wavelength range where the Sun is brightest. We are adapted to the Sun's light in the most literal possible sense. The Sun appears white to eyes calibrated to its spectrum, though it appears yellow when viewed through the atmosphere because shorter blue wavelengths are scattered more effectively by atmospheric molecules, removing them from the direct solar beam and redistributing them across the blue sky. Cool stars, red dwarfs like Proxima Centauri, have surface temperatures of 2,500 to 4,000 Kelvin. At these temperatures, the peak of the blackbody spectrum falls in the near-infrared, and the visible light emitted is weighted toward the red end of the spectrum. Hence, red dwarfs appear orange-red to the eye. Most of their energy is in wavelengths we cannot see, in the infrared. A planet around a red dwarf would receive most of its stellar energy in the near-infrared rather than in visible light. Photosynthesis on such a planet, if it exists, would need to be adapted to infrared wavelengths rather than visible wavelengths. Hot stars, massive blue stars called O-type and B-type stars, have surface temperatures of 10,000 to 50,000 Kelvin. At these temperatures, the peak emission falls in the ultraviolet, wavelengths even shorter than visible light. These stars appear blue-white to the eye because their visible emission is strongly weighted toward the blue end of the spectrum. They are enormously more luminous than the Sun. An O-type star may have a luminosity 100,000 times the Sun's. But they are also short-lived, consuming their fuel so rapidly that they can last only a few million years compared to the Sun's 10 billion year main sequence lifetime. A planet in the habitable zone of an O-type star would have only a few million years before the star died explosively as a supernova. Probably not enough time for complex life to develop based on Earth's timescale. The diversity of stellar temperatures reflects the diversity of stellar masses. Stars form over a continuous range of masses from about 0.08 times the Sun's mass, the minimum mass to ignite hydrogen fusion, up to approximately 150 times the Sun's mass, at the theoretical maximum before radiation pressure and instability prevent further growth. This range of masses produces the diversity of temperatures, luminosities, lifetimes, and colours that populates the night sky with stars of different characters. And all of them, from the coolest red dwarfs to the hottest blue supergiants, are surrounded by the same cold space. The coldness of the cosmic background is universal. It does not vary near hot stars and cool stars. It permeates the universe at 2.7 Kelvin everywhere, and the space between and around all stars sits at that background temperature, with local exceptions only at the surfaces and in the immediate atmospheres of the stars themselves, and in the objects warmed by their radiation. The cold of space is not a local property of our particular solar system. It is a cosmic property. It is the temperature of the universe itself, of the photon gas that fills all space and that was set by the expansion and cooling of the Big Bang over 13.8 billion years. Every star in the observable universe is embedded in this cold. Every star heats what its radiation touches and leaves the surrounding space cold. The contrast between stellar surfaces at thousands of degrees and the surrounding space at 2.7 Kelvin is not unique to the Sun. It is the universal condition of every star that has ever existed. This contrast between the hot and the cold, between the concentrated energy of fusion and the diffuse cold of cosmic expansion, is itself a consequence of the universe's origin and history. The Big Bang produced a hot, dense state, and the universe has been expanding and cooling ever since. The stars formed as gravity condensed matter into dense concentrations where nuclear fusion could ignite, local reversals of the universal cooling trend. Each star is a temporary pocket of concentrated energy in a universe progressively approaching equilibrium. The cold of space is the universe's equilibrium state. The hot stars are the departures from equilibrium, local, temporary, powered by the gravitational energy of condensing matter and the nuclear energy of hydrogen fusion. The stars will eventually exhaust their fuel. They will die and cool. Their remnants, white dwarfs, neutron stars, black holes, will remain, but they will cool over trillions of years. The white dwarfs will fade. The neutron stars will slow their rotation and dim. The universe's temperature will continue to drop toward the cosmic background, as the cosmic background itself continues to cool with the expansion of the universe. In the ultimate future, after trillions of times the current age of the universe, the last stars will have burned out, the last white dwarfs will have cooled, and the universe will approach a uniform temperature close to absolute zero. The hot and the cold will have finally equalized. But we are not there. We are in the middle era, the stellar era, the brief, in cosmic terms, period when the universe contains billions of galaxies, each containing billions of stars, each burning at thousands to millions of degrees, all embedded in the cold fabric of space at 2.7 Kelvin. You are in it right now. The Sun is burning 400 million kilometers away, or 8 light minutes in more useful units. Its radiation is passing through the space between you and it at the speed of light. That radiation is not warming the space it passes through. It is arriving at Earth's atmosphere and surface and warming them, warming you if you are in sunlight. And outside Earth's atmosphere, just above the thin shell of air that moderates your world's temperatures and makes your existence possible, the space through which that sunlight has just travelled is cold. Colder than liquid nitrogen. Cold enough that an unprotected human body would freeze and simultaneously overheat on different sides simultaneously. Cold enough to freeze the gases that your breath is made of. Cold enough that only the engineering of spacecraft life support systems makes it survivable by biological beings in thin metal and polymer shells. The Sun is hot. Space is cold. They are both true at the same time, because heat is about particles moving, and space has essentially no particles to move. Because radiation heats what it hits, but not the nothing it passes through, because temperature requires something to have a temperature, and the vacuum of space is almost nothing, because the cold of the cosmic background is the residual signature of the universe's birth 13.8 billion years ago, and it fills everything that is not specifically being heated by something else. Understanding why space is cold when the sun is hot is understanding something fundamental about the nature of heat and the nature of emptiness and the nature of the universe itself. A universe in which concentrated pockets of burning fusion reactions exist against a background of cosmic cold, separated from that cold by nothing but the vacuum through which their light travels without warming it. This is the universe you live in. A hot star 8 light minutes away. A cold void between you and it. An atmosphere thin enough that you can see the stars at night through it, but dense enough that it moderates the temperature extremes of sunlight and shadow to the range within which biology operates. A planet whose geological processes and magnetic field and atmospheric chemistry have conspired over billions of years to maintain that moderation against a slowly brightening sun and an unforgiving cosmic background. You are in a narrow zone of warmth in an overwhelming cold. The warmth is maintained by a star that will burn for another 5 billion years. The cold extends in every direction from here to the edge of the observable universe and beyond. The zone of warmth is your solar system, your planet, your atmosphere, your body. Everything outside that zone is cold in a way that makes every human concept of cold inadequate to describe it. And the light from that hot star is passing through that cold right now, on its way to you, not warming the space it crosses, carrying its energy across 8 light minutes of cosmic cold to deposit it in your atmosphere and your surface and your skin, and in doing so, making possible everything that you are and everything that has ever lived on this planet. Let us talk about what happens to heat in the very early universe, because the current cold of space is not the universe's natural state. It is the result of 13.8 billion years of expansion and cooling from a beginning that was not cold at all. Understanding the thermal history of the universe, how it went from unimaginably hot to unimaginably cold, illuminates something profound about why heat and cold are distributed the way they are today. In the first fraction of a second after the Big Bang, the universe was not merely hot. It was at temperatures so extreme that the concepts we normally use to describe heat break down entirely. At one Planck time after the beginning, approximately 10 to the power of negative 43 seconds, the temperature of the universe was approximately 10 to the power of 32 Kelvin. 100 million trillion Kelvin. At this temperature, the energy density was so extreme that all 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, are thought to have been unified into a single interaction. The distinction between matter and radiation was meaningless because everything was radiation, energy so concentrated that the concepts of particle and wave, of matter and light, had no separate meaning. As the universe expanded, these temperatures dropped with extraordinary rapidity. At 1 microsecond after the Big Bang, the temperature had fallen to approximately 10 to the 13th Kelvin. Still incomprehensibly hot, but cool enough that quarks had condensed into protons and neutrons. At 1 second, the temperature was approximately 10 billion Kelvin, cool enough that electron-positron annihilation was occurring faster than pair production, leaving the small excess of electrons over positrons that constitutes the matter of the universe. At 3 minutes, the temperature had fallen to approximately 1 billion Kelvin, cool enough for nuclear fusion to occur in the expanding plasma, fusing protons and neutrons into helium nuclei and traces of lithium. This is Big Bang nucleosynthesis, and it is responsible for the fact that approximately 25% of the ordinary matter in the universe is helium rather than hydrogen. The helium was produced in the first 3 minutes of cosmic time. After 3 minutes, the temperature continued to fall and the density continued to drop with the expansion. Nuclear fusion ceased. The universe was no longer hot and dense enough to sustain it. For the next 380,000 years, the universe was a hot, opaque plasma of ionized hydrogen and helium, a fog of charged particles that scattered photons and prevented them from traveling freely. The universe was bright everywhere and opaque everywhere simultaneously. Photons couldn't go anywhere without being absorbed and re-emitted. Temperature and radiation were in intimate contact, continuously interacting, maintaining a tight thermal coupling between matter and radiation. Then, at 380,000 years, the temperature had dropped to approximately 3000 Kelvin. At this temperature, something crucial happened. The electrons and protons in the plasma were moving slowly enough to combine into neutral hydrogen atoms. Neutral hydrogen is much less effective at scattering photons than free electrons and protons. Within a relatively short time, perhaps a few tens of thousands of years, the plasma cleared. The photons that had been trapped in the plasma were suddenly free to travel. They have been traveling ever since, cooling as the universe expanded, their wavelengths stretching with space. The 3000 Kelvin photons of recombination have been stretched by the 1100-fold expansion of the universe since then, their wavelengths 1100 times longer, their equivalent temperature 1100 times lower. From 3000 Kelvin down to 2.727 Kelvin, the cosmic microwave background. This is the universe's thermal history in broad outline, a beginning at temperatures beyond comprehension, a cooling through nuclear and atomic physics milestones as the expansion diluted the energy, a clearing that released the oldest photons to travel freely, and then hundreds of millions of years of darkness, after recombination but before the first stars, during which the universe continued to cool and the matter condensed under gravity into the first structures that would eventually become galaxies. The first stars are estimated to have formed approximately 100 to 200 million years after the Big Bang. The universe at that time was at a temperature of perhaps a few tens of Kelvin, cold by cosmic standards, but still warmer than today's 2.7 Kelvin, because the expansion had not yet diluted the cosmic background as much as it has today. When those first stars ignited, they were the first local reversals of the universal cooling trend, the first pockets of intense heat in a cooling universe. They were enormous, hundreds of times the mass of the Sun, far larger than most stars formed later, and they burned hot and fast, and died in supernova explosions that seeded the surrounding gas with the first heavy elements. Carbon, oxygen, nitrogen, iron, the materials necessary for planets and for life, did not exist until the first generation of stars died and distributed their nuclear products into the interstellar medium. Every atom of carbon in your body was produced in the interior of a star that died before the solar system formed. Every atom of oxygen you breathe was forged in stellar nucleosynthesis. Every iron atom in your blood was produced in a supernova explosion. You are made of the debris of dead stars, of material that was once at the heart of a nuclear furnace at millions of degrees, dispersed by the violence of stellar death into the cold interstellar median, gathered again by gravity into the molecular cloud that collapsed to form the solar system, incorporated into the Earth, and eventually organized by chemistry and biology into the atoms that constitute your body. The hot and the cold are not separate things in the history of the universe. They are the same process viewed at different scales and different moments. The universe began hot and has been cooling since. The stars are local reversals of that cooling, concentrations of matter dense enough to reignite nuclear fusion and produce new heat from gravitational collapse. The planets are the debris of stellar formation, material that did not make it into the star, organized into smaller bodies by gravity and chemistry. Life, if it is typical of what chemistry produces in the right conditions, is an even more local and more temporary reversal of the cooling trend. A concentration of molecules that captures energy from the nearby star and uses it to maintain local order against the universal tendency toward disorder and cold. We are made of star stuff. The phrase attributed to Carl Sagan is scientifically accurate in the most literal sense. We are atoms that were once in stellar interiors at millions of degrees. We are organized by processes that depend on the energy of a star burning at thousands of degrees 8 light minutes away. We exist in the narrow, warm zone between that star and the cold of space. We are temporary local reversals of the universal cooling that has been proceeding since the Big Bang. And we live in the brief stellar era, the cosmic moment when stars still burn and warmth is still available to the matter organized near them. This perspective on heat and cold, the cosmic perspective, reveals something that the everyday question, how can space be cold if the sun is hot, does not immediately suggest. It is not that the sun is hot and space is cold despite each other. It is that both are expressions of the same physical history. The sun is hot because gravity condensed matter densely enough to ignite fusion, a local concentration of the universe's energy. Space is cold because the universe began hot and has been expanding and cooling for 13.8 billion years, a global dilution of that same energy. The hot and the cold are two aspects of the same universe, seen at different scales. Now let us talk about the absolute zero of temperature, because understanding what it means for something to be at absolute zero illuminates both the nature of temperature itself and the reason why the 2.7 Kelvin of the cosmic background represents a genuine minimum for anything in the universe, rather than an arbitrary reference point. Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, is the temperature at which a system has the minimum possible thermal energy. According to classical physics, it would be the temperature at which all molecular motion ceases, where atoms stop vibrating, electrons stop moving, everything freezes into perfect stillness. According to quantum mechanics, the situation is more nuanced. The uncertainty principle, which states that you cannot simultaneously know both the position and momentum of a particle with perfect precision, means that particles can never be perfectly at rest. Even at absolute zero, particles retain a minimum residual motion, called zero-point motion, that cannot be removed by any amount of cooling. Absolute zero has never been achieved and cannot be achieved in practice. The third law of thermodynamics states that it is impossible to cool any system to absolute zero in a finite number of steps. You can approach absolute zero asymptotically, getting ever closer with ever more sophisticated refrigeration, but never reach it. The coldest temperatures ever achieved in a laboratory are approximately 1/10 billionth of a Kelvin, 100 millionth of 1 millionth of a degree above absolute zero, achieved by cooling small clouds of atoms with lasers and magnetic fields in conditions far more controlled and far colder than anything that exists naturally in the universe. The cosmic microwave background at 2.7 Kelvin is therefore not cold by laboratory standards. Physicists routinely work at temperatures tens of billions of times colder in their experiments. But the cosmic background is cold in the sense that it represents the floor of the natural temperature scale, the temperature that any object in the universe will cool to if isolated from all other energy sources. It is the temperature set by the universe itself, by the photon gas that fills all space, by the cooling of the Big Bang's afterglow over 13.8 billion years of expansion. The cosmic background temperature is not constant. It decreases as the universe expands. The relationship is straightforward. The temperature scales inversely with the scale factor of the universe, which measures how much the universe has expanded. As the universe doubles in linear scale, the temperature halves. The current temperature of 2.7 Kelvin means the universe has expanded by a factor of approximately 1,100 since recombination, when the temperature was 3,000 Kelvin. In the future, as the universe continues to expand, the background temperature will continue to drop, 1 Kelvin in perhaps 100 billion years, approaching zero asymptotically as the universe approaches infinite size. This cooling has profound consequences for the long-term future of the universe. As the background temperature drops, objects cool more efficiently. They can radiate heat to a colder background more readily. White dwarfs, the remnants of dead stars cooling over trillions of years, will eventually reach temperatures comparable to the background, and then effectively stop cooling further, becoming black dwarfs in equilibrium with the cosmic background. In the very far future, after the universe has expanded enormously, the background temperature may drop below the Hawking temperature of large black holes, at which point black holes would begin net evaporation, emitting more radiation than they absorb from the cooling background and slowly shrinking over astronomical timescales. All of this future history is driven by the expansion of the universe, by the same process that diluted the Big Bang's heat from incomprehensible temperatures to the 2.7 Kelvin of today, and that will continue to dilute it toward zero indefinitely. The universe is cooling. It will always be cooling. The stars are a temporary interruption, local heating events that burn for millions to billions of years and then die, returning their matter to the cold interstellar medium. On the largest scales and the longest time scales, the trend is irreversible and universal, toward cold, toward darkness, toward maximum entropy. We happen to exist in the middle of this process, not at the beginning when everything was hot and radiation dominated, not at the end when all stars have burned out and the universe approaches its asymptotic cold. In the middle, the stellar era, when local concentrations of matter have created billions of hot objects that warm the surfaces of the planets near them and make possible the chemistry of life. This middle era is long by human standards. The stellar era will last approximately 100 trillion years. But it is finite. It has a beginning in the formation of the first stars and an end in the death of the last red dwarf. We are living in its early middle section, when the universe is still rich with stellar activity and the light of billions of galaxies still fills the night sky. The cold of space that surrounds our warm stellar neighbourhood is not the universe's imperfection or its failure. It is the universe's dominant state. The warmth of stars is the exception. The cold of space is the rule. And we, conscious, warm-blooded, dependent on the energy of a nearby star for every biological process, are among the rarest consequences of the exception. Temporary local pockets of warmth and organisation in an overwhelming sea of cold. Let us now talk about how temperature is measured in astrophysics, because the techniques astronomers use to determine the temperature of objects they can never visit or touch are themselves a fascinating part of the story of how we know what we know about heat in the universe. The primary tool is spectroscopy. When atoms and molecules absorb or emit electromagnetic radiation, they do so at specific wavelengths, corresponding to transitions between their quantum energy levels. Each element has a characteristic set of these transitions, a spectroscopic fingerprint that is unique to that element. Hot gas emits light at these specific wavelengths, called emission lines. Cool gas absorbs light at the same wavelengths, called absorption lines. By analysing the spectrum of light from a star or gas cloud, an astronomer can determine what elements are present and in what ionization states. The ionization state, how many electrons have been stripped from an atom, depends on temperature. Iron, with 13 electrons removed, requires temperatures of millions of degrees. Neutral hydrogen can only exist at temperatures below about 10,000 Kelvin. Singly ionized helium, helium with 1 electron removed, indicates temperatures above about 25,000 Kelvin. By identifying the ionization states of elements present in a spectrum and matching them to the temperatures at which those ionization states are stable, an astronomer can determine the temperature of the gas producing the spectrum with considerable precision. This technique, used to determine that the solar corona is at million Kelvin temperatures, is called spectroscopic temperature determination. It works for stellar atmospheres, for nebulae, for the hot gas in galaxy clusters, for anything that emits or absorbs electromagnetic radiation in a way that depends on its temperature. It is how we know the surface temperature of stars thousands of light years away. It is how we know the temperature of the intergalactic medium, the extremely hot but extremely dilute gas that fills the space between galaxies in galaxy clusters, reaching temperatures of 10 to 100 million Kelvin, detectable in X-ray observations because gas at those temperatures emits X-ray photons. A complementary technique is black body fitting. Any object in thermal equilibrium emits radiation across a continuous spectrum, the black body spectrum described by Planck's law, whose shape depends only on temperature. By measuring the brightness of an object across multiple wavelengths and fitting the resulting spectral energy distribution to a black-body curve, astronomers can determine the temperature of the emitting surface. This is how the effective temperature of stars, including the Sun's 5,778 Kelvin, is determined. It is how the temperature of planetary surfaces is measured from spacecraft. It is how the 2.7 Kelvin temperature of the cosmic microwave background was measured. The CMB has the most perfect black-body spectrum ever observed in nature, matching the Planck curve at 2.727 Kelvin to a precision of 1 part in 100,000. A third technique uses the Doppler broadening of spectral lines. At any temperature above absolute zero, atoms are moving, their velocities distributed according to the Maxwell-Boltzmann distribution. An atom moving toward the observer emits light that is slightly blue-shifted, compressed to a slightly shorter wavelength. An atom moving away emits slightly red-shifted light. A collection of atoms at a given temperature moves with a distribution of velocities and therefore emits a distribution of wavelengths centered on the line's nominal position. The line appears broadened. The width of the broadening depends on temperature. Hotter gas has atoms moving faster and the lines are broader. By measuring the width of a spectral line and comparing it to the expected width from thermal Doppler broadening, astronomers can determine the temperature of the emitting gas. These techniques together, ionization state analysis, blackbody fitting, Doppler broadening, allow astronomers to determine the temperatures of objects throughout the observable universe without ever being there. They are how we know that the surface of the Sun is 5,778 Kelvin, that the corona is 1 to 3 million Kelvin, that the interstellar medium has multiple phases at temperatures from 10 Kelvin to 1,000,000 Kelvin, that the cosmic microwave background is 2.727 Kelvin, that the intergalactic medium in galaxy clusters is tens of millions of Kelvin, that the core of the Sun is 15 million Kelvin. These temperatures span an extraordinary range, from 2.727 Kelvin for the cosmic background to 15 million Kelvin for the solar core, a factor of about 5 million. Extend it to the most extreme astrophysical temperatures. The shocks produced by the most powerful supernova explosions and gamma-ray bursts can reach 10 to the power of 12 Kelvin, a trillion Kelvin, and the range expands to a factor of nearly 400 billion. From the cold afterglow of creation to the violent explosions of massive stellar death, all of it accessible through spectroscopy, through the detailed analysis of light. This is one of the extraordinary capabilities of electromagnetic radiation as an information carrier. Light from an object carries information about the temperature of that object, encoded in the frequencies and intensities of the photons it emits. Light from a star 4 light-years away carries information about that star's surface temperature, its chemical composition, its rotational velocity, its magnetic activity. Light from galaxies 10 billion light-years away carries information about the temperatures and compositions of the stars they contained 10 billion years ago. The universe is not opaque. It is transparent to the radiation that carries its history. We read that history. Every night, with telescopes on the ground and in space, humans are reading the history of the universe, written in light that has been travelling toward us for billions of years. The coldest parts of that history, the 2.7 Kelvin background, are the oldest parts, carrying information about the state of the universe 380,000 years after its beginning. The hottest parts, the X-ray emission of neutron stars and black hole accretion disks, the gamma rays of supernovae, are the most violent events in the current universe, carrying information about processes occurring in objects whose temperatures exceed anything in ordinary experience. And in between, in the range of temperatures accessible to human experience, from the freezing point of water to the boiling point of iron, almost nothing of astrophysical significance occurs. The universe operates at temperatures either far below or far above the narrow range in which human bodies and human chemistry function. We are adapted to a thermal environment that is astrophysically marginal. warm enough for liquid water chemistry, but cool enough for complex molecular structures maintained by the careful balance of solar radiation and atmospheric greenhouse effect on a planet whose geology and magnetic field have preserved that balance for billions of years. The universe does not know we are here. It does not maintain the warmth of our planet for our benefit. It is doing what it has always done, expanding and cooling, with local concentrations of energy burning briefly against the universal chill. Our star is one of those concentrations. Our planet is one of the objects warmed by that concentration. Our atmosphere is the buffer that converts the extreme temperature difference between direct sunlight and cold space into the moderate range within which biology operates. And we are the temporary result of several billion years of chemistry taking advantage of that buffer. The sun is hot. Space is cold. The gap between them, the 5,775-degree difference between the solar surface and the cosmic background, is what drives all the energy flows that make our world work. Wind and weather are driven by the uneven heating of Earth's surface by sunlight. Ocean currents are driven by temperature differences between tropical and polar regions. Life itself is driven by the capture of solar energy through photosynthesis and its subsequent flow through biological systems. Everything that moves on the surface of this planet, every living thing, every weather system, every ocean current, is powered by the temperature difference between the hot sun and the cold space around it. Remove the cold of space, make space warm, and none of this works. The ability of Earth's surface to radiate infrared photons into space and cool down depends on space being cold enough to accept that radiation without returning as much as it receives. An atmosphere radiates heat to space and cools. An ocean radiates heat to space and cools. A body radiates heat to space through the atmosphere and cools. If space were not cold, if the cosmic background were at the same temperature as Earth's surface, nothing could cool by radiation. The heat would have nowhere to go. The temperature gradients that drive winds and currents and biological processes would flatten. Life, as we understand it, would become thermodynamically impossible. The cold of space is not merely the absence of warmth. It is the condition that makes our warm world possible. It is the heat sink that allows the sun's energy to drive work, to move things, to organize things, to power the chemistry of life, rather than merely accumulating as heat. The hot and the cold are both necessary. The sun provides the energy, space provides the sink, and in the narrow zone between them, on the surface of a rocky planet with a moderating atmosphere, chemistry and biology and consciousness have arisen. You are warmed by a star 8 light minutes away. You are cooled by a space whose background temperature is 2.7 Kelvin in every direction. You exist in the gradient between them, and that gradient, the thermal difference between the hot star and the cold cosmos, is the physical basis of everything that you are and everything that moves and lives on the world you inhabit. This is the answer to the question. Space is cold because radiation does not warm the vacuum it passes through. Space is cold because the universe has been expanding and cooling for 13.8 billion years. Space is cold because the cosmic microwave background, the afterglow of the Big Bang, permeates all of space at 2.7 Kelvin and sets the floor below which nothing can cool by radiation alone. And the sun is hot because gravity condensed matter into a dense enough concentration to ignite nuclear fusion, a local reversal of the universal cooling that has been burning for 4.6 billion years and will continue for another 5 billion. Hot and cold, star and void, source and sink. The two ends of a temperature gradient that spans 5 orders of magnitude across 8 light minutes of vacuum, and that powers every process on the only world we know to be inhabited. The most familiar such boundary is the one we have already discussed in another context, the heliopause, the place where the solar wind meets the interstellar medium, where the outward pressure of the Sun's particle output equals the inward pressure of the surrounding galaxy, where the solar system's bubble of hot, tenuous plasma meets the slightly less tenuous, cold interstellar medium. But there are other boundaries in the universe where hot meets cold in ways that are even more extreme and even more physically rich. Consider the surface of a neutron star. A neutron star is the collapsed remnant of a massive star that underwent a supernova explosion. When a star between approximately 8 and 20 times the Sun's mass exhausts its nuclear fuel, the core collapses catastrophically. The collapse takes place in a fraction of a second, perhaps a tenth of a second. The core's temperature during collapse reaches approximately 100 billion Kelvin. Protons and electrons are forced together to form neutrons. The collapse halts when the neutron degeneracy pressure, the quantum mechanical resistance to packing neutrons together any more densely, can support the weight of the overlying material. The resulting neutron star has a diameter of approximately 20 kilometers. It contains between 1.1 and 2.3 times the mass of the Sun. Its density is approximately 4 times 10 to the 17 kilograms per cubic meter, comparable to the density of an atomic nucleus, but extending over a sphere 20 kilometers across. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth. The surface of a newly formed neutron star, created in the immediate aftermath of the supernova, has a temperature of approximately 100 billion Kelvin. It cools rapidly by neutrino emission in the first minutes and hours, and then more slowly by photon emission over thousands of years. An old neutron star, one that formed millions of years ago and has been cooling ever since, has a surface temperature of perhaps 1 million Kelvin, still far hotter than the Sun's surface. And surrounding this million Kelvin object at 20 kilometers diameter, immediately surrounding it, separated from its surface by nothing, is space at 2.7 Kelvin. The boundary between the neutron star's surface and the surrounding vacuum is one of the steepest temperature gradients in the universe. Within a millimeter of the neutron star's surface, the temperature drops from 1 million Kelvin to a few Kelvin, from roughly 200 times the Sun's surface temperature to the cosmic background temperature, across a distance smaller than the thickness of this page. No material boundary mediates this transition. No atmosphere, no convecting fluid, no conducting medium distributes this temperature difference over a more gradual gradient. The neutron star radiates X-ray photons from its hot surface into the cold surrounding space. Those photons travel outward at the speed of light. The space through which they travel remains cold. The transition from million Kelvin surface to 2.7 Kelvin space is essentially instantaneous. The thickness of the boundary is determined by the mean free path of the photons, which in the surrounding vacuum is effectively infinite. There is no boundary. There is surface, and then there is void. And the void is cold. Neutron stars cool over millions of years. Young pulsars, rotating neutron stars that emit beams of radio waves that sweep across Earth like a lighthouse as the star rotates, have been observed to cool from their initial extreme temperatures. The cooling curve, how the surface temperature decreases with time, provides information about the composition of the neutron star's interior, which remains one of the most uncertain aspects of neutron star physics. Does the interior contain exotic matter, hyperons, quark matter, strange matter, or is it composed purely of neutrons? Does it have a superfluid core in which neutrons flow without resistance? The answers to these questions affect how quickly the core can radiate away its thermal energy through neutrino emission, and therefore how fast the surface cools. By observing the temperatures of neutron stars of known ages, astronomers can test these different interior models. This is active current science. Neutron star cooling is an area where X-ray observatories, including Chandra and XMM Newton, have made significant contributions by measuring the surface temperatures of neutron stars and comparing them to theoretical cooling models. The Neutron Star Interior Composition Explorer, NICER, mounted on the International Space Station specifically to study neutron star physics through X-ray timing observations, has contributed measurements of neutron star radii and masses that constrain the equation of state of dense nuclear matter in ways that are directly relevant to understanding how neutron stars cool. The boundary between the million Kelvin neutron star surface and the 2.7 Kelvin void is real and physical and being actively studied. It is the most extreme temperature boundary that exists naturally in the universe, more extreme than the Sun's corona, more extreme than any supernova shockwave, more extreme than any astrophysical phenomenon except the brief aftermath of neutron star mergers and the most energetic gamma-ray burst fireballs. Now let us talk about black holes and temperature, because black holes introduce an aspect of temperature in space that is genuinely counterintuitive, even to physicists, and that represents one of the deepest connections in theoretical physics between thermodynamics, quantum mechanics, and general relativity. For most of the history of physics since their theoretical prediction through Einstein's general relativity in 1916 and observational confirmation throughout the 20th century, black holes were understood to be thermodynamically inert. They absorb everything that crosses their event horizon, matter, radiation, information, and emit nothing. A perfectly absorbing object in thermodynamics is called a black body, and a black body at thermal equilibrium emits radiation at a rate and spectrum determined by its temperature. But if a black hole emits nothing, it has no temperature in the thermodynamic sense. It seemed to violate the laws of thermodynamics in a specific way. It could absorb entropy from infalling matter, but could not emit entropy, so the total entropy of the universe, including the black hole, would decrease when matter fell in. This violated the second law of thermodynamics, which states that total entropy never decreases. This problem was resolved, partially and controversially, by Stephen Hawking in 1974. Hawking showed that when the principles of quantum mechanics are applied to the region near a black hole's event horizon, black holes are not perfectly cold. They emit radiation, now called Hawking radiation, at a temperature inversely proportional to their mass. The physical mechanism involves quantum vacuum fluctuations near the event horizon. In quantum field theory, particle-antiparticle pairs are continuously appearing and annihilating throughout space. Near the event horizon of a black hole, one particle of such a pair can fall inside the horizon while the other escapes to infinity. The escaping particle carries energy away from the black hole, energy that ultimately comes from the black hole's own mass through the gravitational field, and constitutes a real emission of thermal radiation at the Hawking temperature. The Hawking temperature of a black hole is extraordinarily small for any black hole of astrophysical size. For a black hole of 1 solar mass, the Hawking temperature is approximately 60 nanokelvins, 60 billionths of a Kelvin, far colder than the cosmic microwave background at 2.7 Kelvin. A solar mass black hole is colder than space itself. It absorbs more from the cosmic background than it emits as Hawking radiation. It is effectively gaining energy from the surrounding cold, rather than losing energy to it. Such a black hole will not evaporate. It will grow, slowly, by absorbing the cosmic background radiation. The current universe is too hot at 2.7 Kelvin for any stellar mass or supermassive black hole to evaporate. All astrophysical black holes are colder than the cosmic background and are therefore growing rather than shrinking. Only black holes less massive than approximately 10 to the power of 22 kilograms, roughly the mass of a mountain compressed to nuclear density, would currently be hot enough from Hawking radiation to overcome the cosmic background and begin net evaporation. No black holes this small are known to exist. The smallest known black holes are approximately stellar mass. In the far future, after the universe has expanded enormously and the cosmic background temperature has dropped far below the Hawking temperatures of even very large black holes, the black holes will begin to net evaporate. A black hole of 10 solar masses would evaporate completely in approximately 10 to the power of 74 years. A supermassive black hole of 10 billion solar masses would take approximately 10 to the power of 104 years. These timescales are so long they make the current age of the universe look like a brief instant. But they are finite. Eventually, even the largest black holes will evaporate, emitting their mass as Hawking radiation, ending as a burst of high-energy particles as the final stages of evaporation produce smaller and hotter black holes, evaporating faster and faster in a runaway process. The final evaporation of the last black holes, in a universe whose cosmic background temperature has dropped to a tiny fraction of a Kelvin, represents the end of the last significant concentrations of mass and energy in the universe. After that, the universe will contain only the diffuse radiation of evaporated black holes and the cosmic background at its extremely low temperature, asymptotically approaching, but never reaching, absolute zero. A universe of extraordinary coldness and extraordinary uniformity, maximum entropy, minimum structure, the heat death. The Hawking radiation of black holes connects temperature, gravity, quantum mechanics and thermodynamics in a way that no other phenomenon does. It is one of the few results that draws on all four of the fundamental frameworks of theoretical physics simultaneously: general relativity for the gravitational effects on the geometry of space-time near the event horizon, quantum field theory for the particle creation mechanism, thermodynamics for the entropy and temperature relationships, and statistical mechanics for the thermal nature of the emission. Despite being theoretical, Hawking radiation has never been directly observed because the temperatures involved for real black holes are so small. It is considered one of the most robust theoretical results in physics, confirmed by multiple independent derivations using different mathematical approaches. The fact that black holes have temperatures, even extraordinarily small temperatures, means that they participate in the universe's thermodynamic evolution. They are not passive absorbers standing outside the laws of thermodynamics. they are thermodynamic objects, subject to the same second law as everything else. Their entropy increasing as they absorb matter, their temperature rising as they shrink through Hawking evaporation in the far future. Understanding black hole thermodynamics has driven some of the deepest developments in theoretical physics of the past 50 years. The holographic principle, the information paradox, the connections between entropy and the geometry of space-time, all growing from the single insight that black holes have temperatures. Let us now go back to the immediate and practical and talk about how the difference between the sun's heat and space's cold is directly relevant to the technological civilization we are building, not in the abstract future, but in the technologies operating right now. Solar energy, the capture of the sun's radiation and its conversion into useful work, is the most abundant energy source available to any civilization in the inner solar system. The sun delivers 1,361 watts per square metre to any surface perpendicular to its direction at Earth's distance. Earth's total cross-section exposed to sunlight at any given moment is approximately pi times Earth's radius squared, roughly 127 trillion square metres. The total solar power intercepted by Earth is therefore approximately 1.73 times 10 to the 17 watts, 173,000 terawatts. Human civilization currently uses approximately 20 terawatts of power from all sources combined. The total solar power intercepted by Earth is roughly 8,000 times human civilization's total energy consumption. This is not energy available for human use. Most of it goes into heating the atmosphere and surface and driving weather and evaporation, but it illustrates the scale of the resource. Solar panels with realistic efficiencies, currently the best commercial panels, achieve approximately 22% efficiency. Research cells have exceeded 47% under concentrated illumination, could in principle provide all of human civilization's energy needs using a tiny fraction of Earth's surface or a collection area in space. The technology of solar energy conversion works precisely because of the temperature difference between the hot sun and cold space, the same temperature difference that we have been discussing. A solar panel converts solar radiation into electricity by exploiting the photovoltaic effect. Photons from the sun with enough energy to excite electrons across the band gap of a semiconductor material create a potential difference that drives current. The efficiency of this conversion is limited by thermodynamic principles related to the temperature difference between the source, the sun at 5,778 Kelvin, and the sink, the environment, at ambient temperature. The theoretical maximum efficiency of a solar cell, called the Shockley-Queisser limit, is approximately 33% for a single junction device, determined by the physics of how a black body at 5,778 Kelvin can drive a heat engine operating against a background at ambient temperature. Solar thermal power, a different technology that uses the sun's heat directly rather than converting photons to electrons, is also limited by thermodynamic efficiency, but in a way that makes the cold of space directly useful. A solar thermal system concentrates sunlight to heat a working fluid, which then drives a turbine. The efficiency of the turbine depends on the temperature difference between the hot working fluid and the cold heat rejection sink. The hotter the working fluid and the colder the sink, the higher the theoretical efficiency. On Earth, the cold sink is limited by ambient temperature, typically 15 to 30 degrees Celsius. In space, where the heat sink is the 2.7 Kelvin cosmic background, the theoretical efficiency of a solar thermal system would be almost perfect. You could heat a working fluid to any temperature you like with concentrated sunlight, and reject its waste heat to a 2.7 Kelvin background for near-perfect thermodynamic efficiency. This is part of the rationale for proposed solar power satellites, systems that would collect solar energy in space and transmit it to Earth as microwaves. Space-based solar power has several advantages over ground-based systems. It is not limited by the day-night cycle, or by weather, or by the atmosphere's partial absorption of solar radiation, and it operates against the cold of space rather than the warm atmosphere of Earth, potentially allowing more efficient rejection of waste heat. These are not science fiction concepts. The first serious engineering studies of solar power satellites were conducted by NASA and the Department of Energy in the 1970s. Multiple countries are currently pursuing space-based solar power as a potential energy source for the second half of the 21st century. The physics is clear. The engineering challenges are substantial, launching and assembling very large structures in orbit, transmitting microwave power beams to Earth efficiently and safely, maintaining and operating systems over long periods. But the fundamental thermodynamic basis is the same temperature difference that makes all solar energy possible: the hot sun and the cold space. Beyond solar energy, the temperature difference between stars and space is relevant to every energy source in the universe. Life itself is a thermodynamic engine operating between the sun's heat and the cold of space. Every biological process, metabolism, photosynthesis, nerve conduction, muscle contraction, is ultimately driven by the flow of energy from the hot stellar source through the chemistry of organisms and out into the cold environment. Plants capture solar photons at visible wavelengths, high temperature, high energy photons from the 5778 Kelvin solar surface, and convert them into chemical energy. That chemical energy flows through food chains. Animals metabolize food, releasing the stored chemical energy as heat, low-energy infrared photons that they radiate into the environment, ultimately into space. Every living thing is a machine for converting high-quality hot source photons into low-quality cold sink photons, while capturing some fraction of the energy flow to maintain its own organization. The cold of space is not merely the passive background against which life occurs. It is the active participant that makes the thermodynamic conversion possible. Without a cold sink, there can be no thermodynamic engine. Without a thermodynamic engine, without the ability to extract work from an energy flow, there can be no life. The cold of space is as essential to your existence as the heat of the sun. This connection between the temperature difference of the sun and space and the possibility of life is one of the most fundamental thermodynamic facts about our situation. We are not merely warmed by the sun, we are powered by the temperature difference between the sun and the surrounding cold. We are thermodynamic engines running on that difference. Our metabolism, our nervous system, our consciousness, all are sustained by the flow of energy from hot source to cold sink across the 150 million kilometers of vacuum separating us from our star. Understanding this connection, really understanding it, not just noting it as an interesting fact, changes how the relationship between the sun's heat and space's cold feels. They are not two separate facts requiring separate explanations. They are two aspects of a single thermodynamic situation that makes life possible. The sun provides high-quality energy. Space provides a cold sink. Life, and everything that moves and changes on the surface of a habitable planet, exists in the gradient between them. Let us talk about what specific temperatures feel like physically, about the phenomenology of cold in space, and how our bodies and instruments register the temperatures we have been discussing, because bringing the abstract numbers into contact with physical experience illuminates them in a way that pure physics cannot. Absolute zero, the theoretical minimum, corresponds to a state in which there is no thermal motion whatsoever in matter. You cannot feel absolute zero because the process of feeling requires thermal interactions between your body and the environment, and at absolute zero there are no thermal interactions. You would simply stop. Every biological process requiring thermal energy would cease simultaneously. Not dramatically, not with sensation, simply stop. At 2.7 Kelvin, the cosmic background temperature, the situation is similar but not identical. 2.7 Kelvin represents a real temperature. Matter at 2.7 Kelvin does have thermal motion, however slight. Helium, the only substance that remains liquid near absolute zero at standard pressures due to quantum effects, liquefies at 4.2 Kelvin and becomes superfluid, flowing without viscosity at 2.17 Kelvin. Cosmic background temperature is below both of these phase transitions. Helium at 2.7 Kelvin would be a superfluid. Hydrogen, the most common element in the universe, solidifies at 14 Kelvin and would be a solid at 2.7 Kelvin. All ordinary gases would be solid. The only things that remain gas phase at 2.7 Kelvin are photons, radiation, and the trace amounts of exotic matter like dark matter, whose interaction properties keep it from condensing at any temperature. A spacecraft in deep space, far from any star, reaches temperatures approaching the cosmic background asymptotically, cooling by radiation toward 2.7 Kelvin, but never quite reaching it because the cosmic background photons provide a constant heat input that balances the spacecraft's own radiation at that floor temperature. The actual equilibrium temperature of a spacecraft far from any star would be 2.7 Kelvin, plus a small correction from whatever small heat sources exist internally. Radioactive decay of trace elements in the materials, cosmic ray impacts, internal electronic systems, if any, are operating. At liquid nitrogen temperatures, 77 Kelvin, materials behave dramatically differently from their room temperature properties. Metals become more brittle. The ductile to brittle transition in steel occurs around 100 Kelvin, which is why welded steel structures in Arctic environments can fail catastrophically in extreme cold. Rubber and many polymers become glassy and brittle. Biological tissue, already dead at such temperatures, becomes rigid as ice crystals form throughout. The Challenger Space Shuttle disaster in 1986 was partly caused by the failure of rubber O-rings at the freezing temperatures of that January morning, temperatures of minus 13 degrees Celsius, far above liquid nitrogen temperature, but cold enough to make the rubber less elastic than its design required. The lesson was that materials behave in thermally sensitive ways that must be understood across the full range of temperatures the system will experience. At the temperature of the Moon's sunlit surface, 127 degrees Celsius, lead softens slightly and becomes distinctly easier to work. Tin undergoes a phase transition, tin pest, if cycled between warm and cold temperatures, crumbling from the metallic beta phase to the non-metallic alpha phase. Most organic materials degrade rapidly over geological timescales at these temperatures. Water boils at sea level pressure at 100 degrees Celsius, meaning liquid water would instantly vaporize in the full moon's sunlit environment if there were any water present on the surface. The rocks of the lunar surface, expanded by heating, crack and fracture differently than they would at lower temperatures, producing the characteristic gravel and regolith of the lunar surface partly through thermal cycling. At the temperatures of the solar corona, 1 to 3 million Kelvin, all ordinary matter is fully ionized. No atoms retain any electrons. The material is a pure plasma of bare atomic nuclei and free electrons. Chemical bonds are impossible. The thermal energies involved are thousands of times larger than any chemical bond energy. Nuclear reactions are possible but not inevitable. At 1 million Kelvin, the thermal energies of protons are still below the Coulomb barrier that prevents fusion in most encounters, though rare high-energy collisions in the tail of the Maxwell-Boltzmann distribution can occasionally fuse. It is at 15 million Kelvin, in the solar core, that the collision energies are high enough that quantum tunneling through the Coulomb barrier allows the sustained nuclear fusion that powers the Sun. At the temperatures of supernova shocks, up to 100 billion Kelvin, protons and neutrons are forced together to form nuclei in a process called rapid neutron capture, the R process, that produces the heaviest elements in the universe. Gold, platinum, uranium, these elements cannot be produced in ordinary stellar nucleosynthesis. They require the extreme neutron densities and temperatures available only in supernova explosions and in neutron star mergers. The gold in your jewelry was forged in the collision of two neutron stars somewhere in the galaxy billions of years ago and dispersed into the interstellar medium by the explosion, eventually incorporated into the molecular cloud that collapsed to form the solar system, and eventually concentrated by geological processes into the veins and deposits from which it was mined. These temperature ranges, from 2.7 Kelvin to 100 billion Kelvin, span the universe's thermal landscape. Every temperature in this range corresponds to different physics, different chemistry, different material properties, different astronomical phenomena. And they all coexist in the universe simultaneously. The cold background and the hot stellar interiors, the neutron star surfaces and the interstellar medium, the planetary atmospheres and the supernova shocks, all existing at the same moment, all connected by the flow of radiation from hot to cold, all participating in the thermodynamic evolution of the universe from its hot beginning to its cold ultimate fate. We measure all of it with thermometers and spectrographs and bolometers and X-ray detectors and radio receivers. We have mapped the thermal landscape of the universe from the cosmic background to the hottest objects known. We have instruments that operate within fractions of a degree of absolute zero, and instruments that detect radiation from objects at temperatures of trillions of Kelvin. We are a species that evolved in a narrow thermal range between about -50 and +50 degrees Celsius that is astrophysically almost meaningless, and we have extended our reach with instruments to probe every temperature the universe contains. This extension of reach, this ability to measure and understand phenomena at temperatures utterly beyond any direct human experience, is one of the extraordinary achievements of theoretical and experimental physics. Understanding black hole temperatures required combining general relativity with quantum field theory in ways that are still not fully reconciled into a consistent theory of quantum gravity. Understanding the cosmic background required understanding the physics of the early universe at temperatures of thousands of Kelvin and tracing its cooling over 13.8 billion years. Understanding stellar interiors required solving the physics of nuclear reactions and radiative transfer at temperatures of millions to hundreds of millions of Kelvin. All of this done by minds adapted to a world between 0 and 100 degrees Celsius, using instruments and mathematics to reach beyond the limits of direct experience. The question, how can space be cold if the sun is so hot, is a question that leads, if followed seriously, to every aspect of thermal physics, to the nature of heat, to the mechanisms of heat transfer, to the laws of thermodynamics, to the structure of stars, to the thermal history of the universe, to the nature of black holes, to the ultimate fate of the cosmos. It is a question whose answer encompasses virtually all of physics and astronomy and cosmology, if you pursue it far enough. It is also a question that has a simple, short answer. Radiation does not heat vacuum, only objects, and a deep, long answer that takes you through the entire thermal structure of the universe, from the 15 million Kelvin solar core to the 2.7 Kelvin cosmic background. Both answers are true. The short answer is the correct one for everyday purposes. The long answer is the correct one for understanding why the universe is organized the way it is, why stars are hot and space is cold, and planets exist in the gradient between them, and life has arisen in that gradient on at least one rocky world, 8 light minutes from one particular star in one particular galaxy, among the hundreds of billions of galaxies in the observable universe. We are here because the sun is hot and space is cold. We are here because the energy flowing from the hot source to the cold sink can be captured by chemistry and organized into biology. We are here because a planet in the right orbital range around the right type of star accumulated the right kind of atmosphere to moderate the temperature extremes of a world simultaneously blasted by solar radiation on one side and facing the cold cosmos on the other. We are here because the 13.8 billion year cooling of the universe from its hot beginning produced in its middle era the conditions under which stars can burn and planets can warm and chemistry can complexify into something capable of looking at the temperature of space and asking why it is what it is. The question has been asked. The universe continues to cool. The sun continues to burn. The cold continues to surround our warm world in every direction. And we are here in the gradient, warm and curious and temporary, asking questions whose answers require understanding the entire thermal history of everything. There is a particular moment that happens when you are outside on a clear night and you look up at the stars and you feel the cold. Not the cold of the air. The air is its own thing, a thin, warm blanket draped over a planet, a local exception to the universal condition. The cold behind the air. The cold you can almost sense in the direction of the sky, even on a warm summer night. The sense that above the atmosphere, above the few kilometers of gas that give you weather and blue sky and breathable air, there is something vast and dark and cold in a way that the word cold barely describes. That sensation is accurate. You are sensing something real. The cosmic background at 2.7 Kelvin is there. The vacuum through which the sun's light has just travelled is there. The void that extends from the edge of the atmosphere to the edge of the observable universe and beyond, cold, dark, nearly empty, indifferent, is there. You are separated from it by a few kilometers of gas whose total mass is pressing down on you at about 100,000 pascals of atmospheric pressure. That gas is all that stands between you and the cold behind the stars. And simultaneously, in a direction you cannot look at directly because it would damage your eyes, the sun is burning, right now, at this exact moment. 600 million tons of hydrogen converted to helium every second. 100 billion nuclear bombs per second. A surface at 5,778 Kelvin, emitting light at a rate that, even spread over 150 million kilometers of expanding sphere, still delivers 1,361 watts to every square meter of surface on this planet facing it. Every photon of that energy that reaches you was produced somewhere in the solar interior over a timescale of tens of thousands to hundreds of thousands of years, as it slowly diffused outward from the core through the radiative zone and then travelled the final 150 million kilometers in 8 minutes and 20 seconds before hitting your skin and depositing its energy as warmth. The energy you feel from sunlight is old. It was produced in nuclear reactions in the solar core perhaps 100,000 years ago, and has been slowly working its way to the surface ever since. The solar photons arriving at Earth today were born in the Sun during the last ice age, when humans were painting caves in Europe and crossing land bridges into the Americas. That ancient energy is what warms you. That ancient energy is what drives the weather and the oceans and the photosynthesis and the food chains and the metabolism of every living thing on this planet. And between you and the source of that energy, between the warm surface where you stand and the hot furnace that produces the energy, is cold. Not warm, not intermediate. Cold in the most extreme sense. Cold enough to solidify oxygen. Cold enough to solidify nitrogen. Cold enough that any water exposed to it would instantly sublimate, skip the liquid phase entirely, and become vapor that would then freeze onto any nearby cold surface. Cold enough that an unprotected human body would cool by radiation faster than any physiological process could compensate, reaching fatal temperatures within minutes on the shaded side, while the sunlit side heated to temperatures that would cook tissue. This coexistence, the hot star and the cold void separated by nothing, is not a paradox. It is the natural consequence of what heat is and what vacuum is and how radiation works. Heat requires particles moving. Vacuum has essentially no particles. Radiation heats what it hits, but not the nothing it passes through. The sun heats objects. It does not and cannot heat space. The space between the sun and those objects remains at the cosmic background temperature that has been set by the expansion and cooling of the universe over 13.8 billion years. Understanding this is understanding something fundamental about where you are. You are at a specific location in a specific solar system at a specific moment in the thermal history of the universe. The universe began hot, incomprehensibly, unimaginably hot, and has been cooling ever since. The stars are local reversals of that cooling. Concentrations of matter dense enough to reignite nuclear fusion. Temporary pockets of extreme heat in an expanding cold universe. Your sun is one of approximately 200 billion such pockets in your galaxy alone. There are approximately 1 trillion galaxies in the observable universe. Each galaxy contains billions to hundreds of billions of stars. Each star is a hot point in the cold void, and the cold void is by far the dominant condition. The stars are so small and so sparsely distributed that they occupy a negligible fraction of the universe's volume. You are on a planet orbiting one of those hot points. Your planet has an atmosphere that moderates the temperature difference between the hot star and the cold void, converting the extreme thermal environment of direct starlight and cosmic cold into the moderate range within which liquid water can exist and chemistry can be complex and biology can operate. Your planet has been maintaining this moderation for 4.6 billion years through a combination of orbital geometry, atmospheric composition, geological carbon cycling, and magnetic field protection. The probability of all these factors aligning is not well established. We do not know how common such planets are because we do not yet have the observational capability to characterize the atmospheres of Earth-like planets around other stars. But we know it happened here, at least once, in this solar system, on this planet. The cold of space is 2.7 Kelvin in every direction from where you are. The heat of your star is 5,778 Kelvin at its surface and 15 million Kelvin at its core. The gradient between these temperatures, the flow of energy from hot source to cold sink, powers every biological process in every living thing on this planet. Every heartbeat, every thought, every photon captured by a plant and converted into chemical energy. Every metabolic reaction that maintains your body temperature at 37 degrees Celsius against a cold cosmos that would pull that heat away in minutes if your body stopped generating it. You are a thermodynamic engine. A machine for converting high-quality solar photons into low-quality infrared photons while using the energy difference to maintain local organization against the universal tendency toward disorder. You do this continuously, every second of every day of your life, without ever thinking about it. Your body manages the thermal gradient automatically. Your heart beats, and your lungs breathe, and your cells metabolize, and your neurons fire, and all of it is thermodynamics, the consequence of living in the gradient between a hot star and a cold universe. This is not reductive. Understanding that you are a thermodynamic process does not make you less remarkable. It makes you more remarkable. Because the transition from the simple physics of heat and cold, radiation does not warm vacuum, stars heat objects, the universe is cooling, to the extraordinary complexity of a conscious being asking why space is cold, is not a small step. It is perhaps the most extraordinary step in the known history of the universe. From physics to chemistry to biology to consciousness to the question of where you are and what surrounds you and why it is cold. The sun is hot because gravity made it so. Space is cold because the universe has been expanding and cooling for 13.8 billion years. You are warm because you are a biological system capturing the energy flowing from the hot star to the cold void and using some fraction of that flow to maintain your improbable organization against the universal tendency toward cold and disorder. And you are here, in the gradient, in the narrow, warm zone between the burning star and the cold cosmos, asking about the cold that surrounds you. The answer is that the sun heats what it touches. It does not heat the space between you and it. The space is cold, with the cold of the universe itself, the afterglow of creation, stretched and cooled by 13.8 billion years of expansion, settling at 2.7 Kelvin as the floor below which nothing can naturally cool. That cold is the backdrop against which everything burns, every star, every planet, every biological process, every thought. The cold makes the heat meaningful. Without the cold sink, there is no thermodynamic engine. Without the thermodynamic engine, there is no life. The cold is not the absence of the sun's warmth. It is the condition that makes the sun's warmth useful. It is the other end of the gradient that powers everything. You are warm. Space is cold. The sun is burning. And in the gradient between the burning and the cold, in the thin, warm shell of a small, rocky planet at exactly the right distance from exactly the right type of star, something has arisen that can look at the cold and understand it. That understanding is what you are, made of star stuff. Powered by the sun, cooled by the void, alive in the gradient. That is enough. That has always been enough. That is, in the end, everything.